In this lecture video, I'd like to introduce the topic of magnets and magnetism. But before we talk about magnetism, I'd like to revisit the idea of how we represent vectors on a two-dimensional screen or page or chalkboard or whatever. An arrow pointed to the left represents that a vector quantity has a direction pointed to the left, and an arrow drawn to point upward indicates that the quantity has a direction upward. But how do you represent that a vector is pointed into the page or out of the page? Up till now, we've mostly gotten away with just not doing that. If a car is driving directly away from you, then instead of drawing that its velocity vector is pointed away from you, we would usually reframe the drawing so that we could see the vehicle pointed left to right, changing the position of the observer. This becomes more complicated with certain topics where you need to be able to see what's happening in 3 dimensions. So on this screen, right now, you see on the left side the symbol we use to represent that a vector is pointed into the page or into the screen. And on the right side, you see the symbol we use to represent that a vector is pointed out of the page or out of the screen. Now, for the topic of magnetism, we should start by noting that any magnet has 2 ends. One is called the North Pole and one is called the South Pole. The North Pole of a magnet points toward the geographic North Pole of the planet Earth, if you put the magnet in a position where it is free to spin around, for example, like in a compass. The south end of a magnet, therefore, points toward the South Pole of the planet Earth. Of course, if the North Pole of a magnet is pointed toward the geographic North Pole of the planet, that must indicate that the North Pole of our planet is actually a magnetic south. We know that to be true because with magnets, north of one magnet will be attracted to south of another magnet. Opposite poles attract, and the north of one magnet will be repelled by the north of another magnet, like poles repel. I want to warn you, north and south do not attract a positive charge, and north and south do not attract a negative charge. This behavior of attracting the opposite and repelling like is the same type of behavior we see with positive charges and with negative charges, but do not confuse magnets with electric charge. This becomes especially difficult because electricity and magnetism are related forces, hence the term electromagnetism. As with masses that form gravitational fields, and as with electric charges that form electric fields, magnets form magnetic fields, which are regions of space around a magnet in which other magnets would feel a magnetic force. On the left side of this screen, you'll see a coil of wire, a lot like on a spiral notebook. This does not create a magnetic field, but if current runs through that wire, that current does make a magnetic field, which looks a lot like the field around a bar magnet, which is just a piece of metal that is magnetic and does not have electric current to make that magnetic field occur. Not all metal is magnetic, and coils without current in them are not magnetic. The symbol for a magnetic field is a capital B. We sometimes refer to magnetic fields as B fields. The magnetic field is a vector field, meaning at any location in space, I can find a vector B for the magnetic field. The loops on this screen are not the vectors. Vectors cannot bend. They point in a straight line. These loops show the direction that the B field points at any particular location near a bar magnet. Inside a bar magnet, the magnetic field points from south to north, and outside of the bar magnet, the magnetic field loops around to point from the north to the south, or into another magnet's south if another magnet's south is closer. I want to emphasize again, electric current makes a magnetic field. Electric charges do not make a magnetic field. Moving charges do. Without the motion, the magnetic field is not created. The shape of a magnetic field is not radially outward from the electric current. It is concentric, meaning pointed this way, not pointed outward from the current, but pointed in a circular path around it. Now, a magnetic field that is pointed in a circular path around this wire could have one of 2 different directions. Is it circular in a clockwise direction or in a counterclockwise direction? And the answer is that it depends on whether the current is traveling up, as shown in this image here, or if the current were traveling in the other direction, down. If the current were traveling in the other direction, down, then the B field would look the same in terms of the shape as we see here, but the arrowheads would be pointed in the opposite direction. The image on the right here shows an easy way for us to be able to tell what direction the magnetic field is given the direction of the current. That also means that if you're given the direction of the B field, you can figure out which direction the current had been. We refer to this as the right-hand rule for magnetic fields because it requires you to use your right hand, not your left hand. If you take your right hand and put it out in the approximate shape that you see in the image here, aligning your thumb in the direction of current allows your fingers to wrap around the wire in the direction that the B field actually would wrap around. This is sometimes easier if you actually have an object in your hand, like a pen or a pencil. Hold it in this direction with your thumb pointed up, and your fingers will wrap around in a direction that is sort of away from you on the right side and toward you on the left, as seen in this image. However, if the current were pointed downward on the screen, you would have to flip your hand over so the thumb was pointed down, and you would see that your fingers then wrap in a different direction, moving away from you sort of on your left side and back toward you, curling back around on your right. This is also shown on the far right image over here, where you see the B field pointed out, that's a vector out of the screen at you, and in, that's a B field pointed into the screen away from you. If the current were, again, pointed downward, these two would be the exact opposite of what we see here. If this isn't clear to you, I'd like to really encourage you to take a look in the OpenStax College Physics textbook, chapter 22.3. That's where these images are from, and they definitely talk about it in that chapter. I want to note that the B field does not spiral and move like in this little animation. It just points around in a circle, but the animation is still somewhat useful to be able to see the direction of the B field at each point around the wire. This is another way to visualize what the magnetic field around a current carrying wire looks like. If you notice over here, this X indicates the vector of current going into that end of the wire, and then therefore pointing out over here. If you bring a compass or other magnet near this current, it will be deflected by this magnetic field. In fact, that's how magnetism around a current carrying wire was first discovered. This doesn't really work around AC power cords because the direction of current is not constant. So if you're going to try this with a magnet, you'll need to find a DC power supply to try it around. The strength of the magnetic B field is calculated by this equation. B equals mu naught times I over 2 pi r around some long straight wire, where mu naught is a constant that is on our sheet. It is one of those constants that allows the metric system to make sense of the universe. It is called the permeability of free space. I is, of course, the current, and 2 and pi, and r is the distance at any point from the current. Mu naught, the value is 4 pi times 10 to the minus 7th, and the units are teslas times meters per ampere, which indicates that the unit of magnetic field is the Tesla. Again, that's how to calculate the magnetic field around a long straight wire. For example, this wire carries 5.0 amps of current directly toward the top of the screen. Calculate the magnitude of the magnetic field at distances 10 centimeters away and 1 meter away from the wire. The reason we have two different distances here is to emphasize that the R in the equation does matter, and the farther away you get from the wire, the weaker the magnetic field will be. The equation is that the magnetic field B has a magnitude of mu naught times the current divided by 2 pi r, and the direction of the magnetic field will be different at each point in space, pointed into the page or into the screen on the right of the wire, and coming out of the page or out of the screen on the left side of the wire. We'll talk in a future example about how exactly you would report that if asked. But for now, the magnitude of the magnetic field would be found in part A as mu naught, which I just look up as 4 pi times 10 to the minus 7th teslas times meters per amp times the current, 5.0 amps, divided by the quantity 2 pi r, where r was given as 10 centimeters, so 0.1 meters. Notice this 4 pi in the numerator and a 2 pi in the denominator, which does make this a little bit reasonable to calculate. If you didn't have a calculator, you could still do this by hand without having to worry about how many decimal places out to take pi. I get that this comes out to 1 times 10 to the minus 5th teslas is the strength of the magnetic field at 10 centimeters. If I were to calculate this at 1 meter, I do this the exact same way, but the distance goes from being 10 centimeters to 1 meter, which means that the calculation comes out to the B field having a magnitude of 1 times 10 to the minus 6th teslas. That is to say, if you were 10 centimeters away, it would be 1 times 10 to the minus 5th teslas, and if you were 100 centimeters away, that's much farther out. The strength of the magnetic field would be weaker, but the direction would still be defined the same way. That was how to find the magnetic field around a long straight wire. But what do you do if you have a wire that is not a long straight wire? For example, what do you do if you have one that is bent into a circular loop, as is shown here? You can see the current comes in, goes around in a circle, and then exits. And you can also see that we've drawn the right hand of an individual in 3 different locations along this loop. In each of these locations, if the thumb points in the direction of the current, the fingers will wrap around to show the direction of the magnetic field. The magnetic field will point up around one part of the wire and down around another part of the wire. On the inside of the loop, the fingers always point upward, which means if you wrap a wire around in a loop like this, you get a strong upward B field in this part of the loop. How strong it is would be calculated like this. This equation here tells us the magnitude of the B field at the center of a loop is mu naught times I divided by 2r at the center of the loop. And then whether the B field is pointed up or down in this loop depends on whether your current is coming in or out of this wire. If it comes in here and around, or if it comes in here and back around this way. If you aren't sure in a given problem, you use your right-hand rule along the wire to determine whether the B field would point up or down inside the loop. This equation tells you for the center of the loop because we don't really care about on the outside of the loop. That's not why we would make a loop of wire. We would make it to determine what the B field is on the inside. This is especially useful when the loop isn't wrapped around just once, but if the wire is wrapped around in a series of loops. We call this a solenoid, and the equation for the magnetic field on the inside of a solenoid is given as mu naught times lowercase n times the current, where lowercase n is the number of times the loop goes around per unit length, the number of turns per centimeter or turns per meter. There are 2 ways to determine the direction of the magnetic field through this solenoid. One is to place your thumb along the direction right here of the current and see which way your fingers wrap. There's another way to do this that looks like this. If you take your fingers and wrap them in the direction of the current here, your thumb will point in the direction of the North Pole. Again, try this using only your right hand. This may seem more useful when you know what a solenoid is. A solenoid is an electromagnet that can be used as a mechanical switch or latch. In the example shown here, current in the wire makes the solenoid an active electromagnet that pulls a metal rod to the right. But if the electricity is turned off, the spring pushes the rod to the left. So whether this is latched or not, or switched or not, depends on whether there is current through this wire. That's called a solenoid, or rather the coil itself is called a solenoid. An example of how a solenoid calculation works is like this. What current is needed, what amount of current in a 10,000 turns per meter solenoid to produce a magnetic field on the inside of the solenoid of 2.5 teslas? Well, the equation is that the magnetic field is equal to mu naught times lowercase n times current. If my lowercase n is given in terms of turns per centimeter or something like that, I would want to put it in terms of turns per meter. I can rearrange this so that current equals B over mu naught n. The B field is the 2.5 teslas, and then in the denominator we have both the mu naught, 4 pi times 10 to the minus 7th teslas times meters per amp, and the lowercase n, which is the 10,000 turns per meter. This gives me a calculation of current equal to 199 amps. That's how much current would be needed to produce that strong AB field on the inside of this particular solenoid. That's our last slide for this video, and we will talk more about electromagnetism in our next one.